Is everything a vector space? We've already looked at the last few examples and seen that bunches of things are vector spaces, but is everything a vector space? Of course not. If everything were a vector space, then there would be no need for this big, huge, long list of axioms. So not everything is a vector space. Just some examples. Suppose we just look at R2, which we already know is a vector space if we use regular addition and regular scalar multiplication. But let's define a different way of doing things. So let's define addition as take two vectors and add them together to get out the vector AB. In other words, the sum of two vectors is ignore that vector. Well, does this kind of addition, vector addition, turn the set R2 into a vector space? Well, that would mean it would have to satisfy all of the axioms down below. While we're at it, we might as well just define what does it mean to multiply AB by a scalar, and we'll just say it's usual. Ka, Kb. Does this make R2 into a vector space? No. We're going to show why. The problem is not with scalar multiplication. The problem is with vector addition. Not every way of defining vector addition turns R2 into a vector space. So, which of the following axioms fails? We're going to look at commutativity. In other words, if I switch the order in which I add things together, if I swap things around and go CD plus AB, do I get the same thing? No. This would say take the first vector and put it here. Grab the first vector, put it there. Does AB equal CD? No. They're not the same, which means this is not a vector space. R2 is not a vector space using this way of adding vectors. Well, we could look at another one. Suppose we go into R2 and we say, we had a problem last time if we defined AB plus CD to just be that. So let's use usual addition. This will be A plus C and B plus D. So this is usual addition. This is going to satisfy the first four properties. So now what we're going to do is we got to come over here and say, well, how are we going to define scalar multiplication? Well, let's take K and let's times it by AB, and let's suppose this triples the values. So if I take K times AB, let's take it and do 3K A, 3K B. This is a way of defining scalar multiplication. Does it satisfy these axioms? I'm actually just going to look here at scalar multiplication by 1 does nothing. Well, if I multiply by 1, that says I should do 3A, 3B. Did scalar multiplication by 1 do nothing? No, it changed. This is not AB. So again, we have something that is not a vector space. Is every set a vector space? I just want to look at one more. And I'm going to look at polynomials of degree 2. We're going to use addition as polynomial addition. And scalar multiplication is regular scalar multiplication. So this is usual and this is usual. Are polynomials of degree 2 a vector space? Well, in this case, I'm going to show that the sum of two vectors is not a vector in the set of polynomials. So what we're going to do is, suppose I take a vector such as x squared. That is a vector of polynomials. And I take another vector, 1 minus x squared. If I add these two vectors together, this is a polynomial of degree 2, that's a polynomial of degree 2. Their sum, however, is x squared minus x squared 0. It's just 1. This is degree 0. And so the sum of two polynomials of degree 2 is a polynomial of degree 0. So in this case, polynomial addition caused us to leave. We weren't closed. We didn't satisfy the closure axiom. We did not get another vector in our set of polynomials of degree 2. So is everything a vector space? Of course not. But many things are, and we're going to be studying vector spaces throughout the semester. That completes the screencast.